All right, so we are going to compare on this one. Before we did one sample, we did like the percent of orange candies in Reese's Pieces. On this one, we're gonna do two samples. We're gonna do a simple comparison of Skittles and M&Ms. So I'm just gonna come up with some that like we could have done this as a class and like counted up the packages in each, but I'm just gonna come up with one. So let's say like I opened up a bag of Skittles. It had 50 Skittles, and the proportion was 13 out of 50 were orange Skittles. So we're looking for what's the proportion of orange. So 13 out of 50, which is 26%, 0.26. So like what that number is, that's like, you could say that that's the sample proportion, so the p hat of S, like Skittles. So the sample proportion of Skittles equals 26%. And then let's say that with my M&Ms, I got 9 out of 50, which would be like 18%. So that is, the way you could write that is the sample proportion p hat of M for M&Ms. You can just label them like that. You can label them 1 and 2, whatever you want, really. Just makes sense between the two. Okay, so there's my, I'm really wanting to find out, I guess, is do Skittles have more orange or do M&Ms have more orange? So I'm going to do there's my two different ones. I'm going to do the difference between them. So the difference between the sample proportion of Skittles minus the proportion of M&Ms is 26% minus 18% is 0.08, 0.08. So what that is this is just like one sample. Y'all could open up a bag of Skittles and M&Ms and do the difference and get a different number. So this was my number for my one sample, okay? And what we would have done on number 2 is done a whole bunch of different ones. Instead, I've just kind of listed a bunch of hypothetical. So like I'll circle this one in blue is like what I just did, my example here of my one sample of Skittles had 0.08 or 8% more orange candies than M&Ms. Like that's what this blue dot right there means. And so like this is, I kind of wrote it up here. This is like a simulation of a whole bunch of p hat S's minus p hat M's. And so you can see we've got some positive numbers, we've got some negative numbers. So like this number right here means that like when you did Skittles minus M&Ms, it was negative 0.08. That meant that M&Ms was 0.06 or 6% more than Skittles. Like the negative, when you do Skittles minus M&Ms, if it's negative, that means M&Ms was more. Anything that's positive meant Skittles was more. So let's say this is like our class set or whatever, and like this blue one here was the one that I did, like where I got 13 out of 50 and 9 out of 50. Okay, so what does each dot represent? Each dot is just like the p hat S minus p hat M. Like every single one of those dots is just a whole bunch of differences in proportion of orange candies. So what does it is the difference, so like the subtraction in proportion of orange candies, because that's what we were looking for, of orange candies for a sample of Skittles versus a sample of M&Ms. So for one sample of Skittles and one sample of M&Ms. Okay, so every single one of those, like this one right here, let's go for, we gotta do a different color. So I've got red, like this one is 0, so that meant like the proportion of Skittles and M&Ms was the exact same here. Like they were both 20% orange candies. They were both 8%, like whatever they were, the difference in the proportions was the exact same. So they had the same amount of M&Ms. Like every single one of these dots is just a simulation of doing a sample of 50 Skittles, doing a sample of 50 M&Ms, and counting the difference between them. So this is just to try and give us a visual representation of what's going on. All right, on number 4, it asks us to just make a prediction on what's the shape, where's the center, where's the spread, the variability. Okay, so if I'm looking at that picture, this is looking like there's like a tail, it's kind of accumulating. It's looking pretty normal, so I'm not going to try and spell approximate again, embarrass myself in front of Mr. Nelson or whoever the sub is. The center of this, the average, I don't know, looks somewhere like in that 0 to maybe 0.02. So maybe I'll just say anywhere from 0 to like 0.02. That looks to be about the average to me. And then what do you guess the standard deviation is? So standard deviation is like once I get to 2 or 3 standard deviations out, I should be at the end of my normal distribution. So if I'm making a guess, if this is my mean, I don't know, maybe how far does 4 go either way? Maybe let's do like 4 or 5. So maybe I'll just say whatever, 0.04. I'm just guessing. I'm just making a prediction. So maybe I've got a mean of somewhere around 0 to positive, somewhere between 0 and that's not negative, that's positive 0.02. So somewhere in between there, I'm thinking. Okay, so let's actually get the true numbers here. And so, at least in the past, a Google search revealed that 21.6% of Skittles are orange and 20% of M&Ms are orange. So that's what each of those companies are claiming, what the average is on those. Average proportion, percentage. All right, so let's find shape, mean, and standard deviation. So what do we think the shape is? And let's do it for Skittles, and then we're going to do it for M&Ms. And so the shape, I realized I screwed up on the worksheet that I gave y'all that is due tonight or tomorrow, like Tuesday or Wednesday. To check for shape, we want to check and see if it's normal. You do n times p, n times 1 minus p, greater than or equal to 10. So if those are not greater than or equal to 10, which one of them on the homework wasn't, what you have to do is, like, if the population that you sampled from is normal, and we'll go into this more later, if the population is normal, then your sample is normal. What we'll just do, if that's not true, just assume that it's normal. I'm not going to worry about it too much. I shouldn't have put that one on I should have fixed it when I did my key. But okay, let's check, is this normal? So you've got n, so we're doing our sample of 50 Skittles, 50 M&Ms. So 50 times Skittles, Skittles, so 0.216. 50 times 0.7, what would that be? 784? Yep. So you do those, and I think you end up getting like 10.8 and 39.2. So those are greater than 10, so we can say that this is about normal, approximately normal. And then you do the same thing for this one. Do 50 times 20%, 50 times 80%, and you end up getting 10 and 40. So both of those are greater than or equal to 40. So we can also say that the M&Ms by themselves are normal. So the Skittles by themselves are normal, the M&Ms. So when I combine them down at the bottom, the combination of them is going to be normal as well. All right, the mean. What's the mean? So our formula, just to remind you, formula sheet, scroll over. Almost there. There we go. So the formula sheet says that the mean of the p hats is equal to the population proportion. So the mean of the Skittles, of all the samples of Skittles, so that would be like PS, that's what we labeled it, would be the population that we're claiming. So this 21.6. That's where we're going to rest. And then the mean of the samples of M&Ms, so the p hats of M&Ms, should settle in at 20%, because that's what they're claiming the population is. All right. And then for standard deviation, I'm actually just going to do the combination of those below. I'm not going to do it twice. And so we'll just look at that now. So if I go to the next page, number 6, or at least on mine, number 6 on the bottom, says describe the distribution of the difference between the proportions. So like if I combine Skittles and M&Ms, which is what we did over here on the front side, like the combination, what would the shapes mean standard deviation? So what's the shape? So since the shape of both of them we proved was normal, what I can say is it's normal because both of those checked out at greater than or equal to 10. So both did that. So we can say that the combination of them is also normal. All right, for the mean, I want to just point to the formula sheet again. So like on our formulas, you've got, scroll this down. So on the formulas, here is for one sample, but this is for 2. And so you can see the mean for the 2 of them, for p hat minus p hat, is just the parameters, the population parameter minus the other one. So just take the difference of the 2, which in this case is, since we're doing Skittles minus M&Ms, so what's the mean of Skittles minus M&Ms? We said from the Google search that Skittles was 21.6% minus 20% of M&Ms. So what do we expect over time to be the average difference between them? It would be 0.016, or so that's like a 1% positive difference. So like we're expecting a positive 0.016. That means that we're expecting more. You expect more Skittles, more orange Skittles than M&Ms. That's basically what that means. Expect more orange Skittles. Okay, and then obviously it's not always more Skittles, so what's the spread? What's the standard deviation? So what is the standard deviation of the proportion of Skittles minus the proportion of M&Ms? So we look at the formula. Okay, look at the formula. And it looks a lot like the other ones, except you notice we're adding. We never subtract standard deviation. So I do the 1, and so this will be like my Skittles. This will be like my M&Ms. I add them together, do the square root, and go from there. So let's kind of go back. Okay, let's go back to this one. So it says it's equal to everything's square root, and it says it's equal to the p. What is this? It's equal to the proportion of 1, which we're going to do Skittles, so 0.216 times 1 minus p hat, so that's going to be 0.784 divided by the number of sampled Skittles, which was 50. We sampled 50. And then it says to plus divided by the proportion of the second one, which is M&Ms, so 20% times 1 minus that divided by the number you sampled of M&Ms, which we sampled 50 M&Ms too. So both of them were 50. Okay, so you just plug it in, similar to our just formula. Just plug it in what you got. So you got your P, what we're assuming. So we assumed from our Google search that the companies are claiming those. You type those in your calculator, and I got 0.08, or am I at 0.812, so I'll just go 0.081 is our standard deviation. So I expect to have 0.016 more Skittles, but I typically vary 0.081. So there's a good variation between the two. Like, obviously, there can be more orange M&Ms than Skittles. It's not crazy to have that happen in between the two. All right, so let's do number 7. Finish out this problem. It asked us to do something. So these two teachers, Mr. Wilcox and Miss Gallus, calculated a difference between the proportions of 0.08 from their samples. Calculate the probability of getting this difference in the proportions or higher. So the question is, find the probability that you were to get this event or higher, and the event was to get positive 0.08 or more. All right, so let me draw our picture, and we said that this is a normal distribution centered around a mean of 0.016 with a standard deviation 0.081. Okay, and we're asking 0.08 was our sample. How many that or more happened? So how many times does 0.08 or more happen? All right, so now, because it really just acts like what we did on Friday, so I've got the mean difference, the standard deviation of the differences, and the proportion of the differences between the two. So now it's just like do our z-score. So I'm going to standardize this value of 0.08. How far is it from the mean of 0.016 divided by our standard deviation 0.081. Grab a calculator. Point 0.08 minus 6 divided by, and I got a z-score, so z equals positive 0.79. That's about right. So 0.79 is our z-score. And so then what we're going to do is we've got a table of values with these standardized scores on our formula chart. So on the formula chart, go to our z-score, and we go to 0.79. 0.7. Whoa. No. How did you zoom in so much? All right, so 0.79. So 0.79 is where it is right there, 0.7852. So what you get, 0.7852, so 78.52%, but that is, the Z table always goes less than, so that's that value there. And so to get the greater than, I'm going to do 1 minus it, and end up getting 21, just over 21% of the time. So that value, that blue value there, 21% of the time, you get a Skittles value having 8% more Skittles than M&Ms that are orange. So just calculating the difference. So the big thing between one sample and two sample is not the Z-score stuff. That kind of works the same. It's getting the mean and standard deviation. So just making sure to calculate these means, to calculate the standard deviations, using your formulas, and then it kind of solves itself into this normal distribution, and you can kind of keep going in the way that we've done it. But it's good to get more practice, and hopefully, especially like second period, we were kind of rushed, kind of having technical difficulties. So just getting some more examples in might make me feel a little better. So let's do check understanding, and then we'll be done. And then there's a worksheet for you to do. You also need to finish the one from Friday, but there's like a 2-sample one that you can work on today. Let's look at this one. So the Westville High School, there are 315 seniors and 389 juniors. 65% of the seniors have parking passes, while 42% of the juniors have parking passes. The statistics teacher selects a simple random sample of 30 seniors and a simple random sample of 30 juniors. Let P hat S minus P hat J be the difference in the proportions of seniors and juniors that have parking passes. All right, so what is the shape of the sampling distribution? So like if I made a simulation of all these different sample, like what's the outcomes that can happen between the two of them? Where would the mean be, or no, what's the shape of it? So we're trying to prove, we want it to be normal. So let's see if it's normal. So you do the sample size of 30 times, so let's do it for seniors. So times 65% sample size times 1 minus 65%. So that's like, when I've already done it, 19 and a half, 10 and a half. So those are greater than or equal to 10. So our sample size is big enough in comparison to our probability. Let's do it for juniors. So juniors is a sample size of 30 times 42%, 30 times 58%, which is numbers I've already calculated, bigger than 10. So what it means is we can say that this distribution, this simulation that we come up with, that we can do, is going to have a pretty normal shape. It's not going to be perfect, but it's going to be approximately normal. So that's good. Right. B, find the mean. So just using the formula sheet again, the formula sheet says seniors minus the p hat of juniors. It says to do the parameter, the population of seniors minus the population of juniors who have it. So like your sample of juniors who have a parking spot is going to resemble the population of seniors that have a parking spot. So the population is 65%, and the junior population proportion is 42%. So our typical samples are going to represent those to have a difference of 23%. 0.23 is our mean. So the average difference, that's saying that seniors are 23% more, on average, they have a parking pass 23% more than juniors. Like, that's what's gonna happen. Like, on average, they have it. C, calculate and interpret standard deviation. So standard deviation of sample proportion of seniors minus the sample proportion of juniors is, it says to do the proportion of your first thing, which in this case we're doing seniors, so the proportion is 65 minus 1 minus 65, so 35, divided by the sample number, which was 30, and then it says plus the proportion of juniors minus 1 minus the proportion of juniors divided by the sample, which was also 30. So these numbers aren't always the same, like 30 and 30, but like in this case they are. So all of that is square rooted to get 0.1253, so 125. So that's our standard deviation at about 12% standard deviation. All right. I think I'm going to change D actually in the question that it asks us. So D, it says, what is the probability that the difference in sample proportion senior minus junior of students with the parking pass is greater than 30%? So I'm actually going to change it, but let me just write out the picture for that. It's really similar to what we just did. Like here's the mean, which was 23%, and we're asking how many had greater than 30%. So like find that. All right, I'm going to change the question though. Let's say instead it said, what's the probability that, let's like divert up here. What's the probability that we had a sample, so that a sample difference, so that one of these had a difference that had more juniors, so that had more juniors than seniors had it. So what's the probability of that? So I just want to do this one, so let me erase this. So we've still got we proved that we have a normal distribution centered around a mean of 23%. But in this case, if we're saying that there's more juniors, that means that when you do the p hat seniors minus p hat juniors, that this number is like a negative number. So juniors are more. So that means 0 and less than is kind of my cutoff. Like anything less than 0 is my cutoff. So like I'm trying to find all the values in this problem with a mean of 0.23, standard deviation of 0.215. How many are 0 or less? What's the probability? All right, so we're going to do z-score. 0 minus 0.23 divided by 0.125. I got a z-score of negative 1.84. which makes sense. It should be a negative z-score if it's left of the mean. And then let's look up this value in the table. So negative 1.84. Alright, so negative 1.8. And then that would be 0, 1, 2, 3, 4. So 0.0329. 0.0329. That is that percent. That's how much that takes up in decimal form, is that little area right there. So there is a 3% chance that juniors, the difference in junior and senior parking lot, like that juniors have more. So it's not a very good chance with this big of a gap between seniors and juniors. There's not a very good chance that juniors on a given sample have more. Because just relating it back to everything, this is just like a simulation of like infinite amount of all these different, like every single one of these dots under this curve just represent one sample of proportion of seniors minus proportion of juniors. Like here's another proportion of senior minus proportion of junior. So these just represent a simulation of all the different types. And so in 3% of those cases, juniors had more parking passes than seniors in a sample of 30 from this school. So that's kind of the idea. So two samples, proportions, really similar to one sample, except the formula is just double them up. And so you need to do that, put it on your picture, do a z-score, get the table value, and solve. So y'all try that out. Make sure to either turn the paper in if you're in person or do the Schoology work. There's another worksheet that has a couple questions that you're getting today. So work on those and have a good Tuesday.